Now that you've seen some definitions for equilibrium constants, let me show you how you can actually calculate them for different chemical reactions. One of the things that is pretty important to do is kind of a quantitative aspect for the equilibrium constant. And what I mean by quantitative aspect is more like numbers and math, okay? And so what I'm going to do now is give you kind of a method, a procedure for solving many different kinds of equilibrium problems using the same type of relationship. Okay, and so the equilibrium constant is actually very useful in a lot of different situations because it gives us a relationship between the initial amounts that are present in a chemical reaction and how much is present at equilibrium, which we're going to consider like the final amount in a chemical reaction. And the approach that I'm going to show you works for any equilibrium process, whether we're talking about a homogeneous reaction where things are all in the same phase, or we're talking about a heterogeneous reaction, things are occurring in different phases, or maybe we're talking about acid-base reactions, or maybe we're talking about solubilities of things that are barely soluble in water or some other solvent, or even complexation of complex ions and ligands. Okay? All of those different situations, they all have the same approach of how to solve them quantitatively. So what I'll do now is show you how to set these up. So the key approach to solving these problems is to create something called the icebox. Okay? I personally didn't create the term icebox. Okay? Somebody else did. But I like the phrase and so I kept it. Okay? And so the letters ICE in the icebox are actually abbreviations, right? It's an acronym. So the I stands for initial, the C stands for change, and the E stands for equilibrium. Okay, and so the easiest thing to do is to basically put numbers in to this icebox and then set up the expression for the equilibrium constant. So what I'm going to do now is give you an example of how this might work, and then you'll see how to do it pretty much for any instance where you have an equilibrium situation. So let's say you have a chemical reaction like this. Okay, A moles of A and B moles of B are in equilibrium with C moles of C and D moles of D. So the initial amounts, meaning the initial concentrations of these things, might be A0 for A, B0 for B, C0 for C, and D0 for D. Usually, but not always, for the products, the initial amounts are going to be 0. Again, they don't have to be, but usually it is. Okay? And the initial amounts will probably not be 0. So for example, maybe this might be 0.5 if it's a 0.5 molar solution. And maybe this is 1 if it's a 1 molar solution. Okay, so these are typically in molarity, moles per liter. Then, as the reaction proceeds, things change. Okay, so for a chemical reaction that starts with reactants and forms products, concentrations of the reactants are going to have to go down, and the concentrations of the products are going to have to go up. So things are changing. How much are they changing by? Something. Okay, so we'll call it X. But I don't just want to call it X because I have to relate how much things change to each other by stoichiometry. Okay, and so maybe A changes by a certain amount AX, where the little a represents the coefficient right in front when I balanced the chemical reaction. So because the reactants are decreasing, that's going to go down by minus AX. Okay, so that's what I've got here. Similarly, for the other reactant, B, that's going to go down by minus BX, okay, because the coefficient in front of the B was little b. Now, as far as the products go, the products are going up, right? Their concentrations are increasing. So I'm going to make this go up by a certain amount, which I'm going to call CX for C and DX for D. So then at equilibrium, all I have to do is add the two columns, right? The initial amount and the change. So at equilibrium, I'm going to have A0 minus AX for the quantity of A, B0 minus BX for the quantity of B, C0 plus CX for the quantity of C, and D0 plus EX for the quantity for D. Okay, and so just to give you a specific example, let's pretend you had a reaction like this. Maybe H2 plus I2 yields 2 HI. And I tell you that the initial concentration of H2 is 1 molar, and the initial concentration of I2 is also 1 molar. So then I can set up my icebox. The initial amount of this is 1, the initial amount of this is 1. The initial amount of HI, I'm going to assume is 0. Okay, nothing happened yet. This is going to go down by x because there's a coefficient of 1 in front of the H2. This is also going to go down by x. This goes up by 2x because there's a 2 in front of the HI. So then at equilibrium, I just have to add these. Okay, 1 minus x, and 2x. And now the last step is to write down what the equilibrium constant is. Okay, so the expression for the equilibrium constant is simply the concentrations of the products raised to the appropriate stoichiometric coefficient divided by the reactants raised to their stoichiometric coefficients. Okay, so now all I have to do is look at the E part of the icebox and use those in my expression for K. Be very careful. Don't forget to also include the coefficients. Those are going to turn out to be exponents. Okay, and so in my general case, the equation looks a little bit like this. Okay, the equilibrium constant K is going to be C0 plus Cx raised to the C power times D0 plus Dx to the D over A0 minus Ax to the A times B0 minus Bx to the B. It looks very disgusting, but you'll see here in this actual case, it's really not that bad. Okay, and so for example, in this specific case, the concentration of HI is 2x. So I have the quantity 2x, and then I square it because of the 2 as my coefficient. And then for the H2, I have 1 minus x. And for my I2, I also have 1 minus x. So that becomes my expression for the equilibrium constant K.